All right, we can probably get started. Welcome to the final installment of the MSPE graduate seminar series for this semester. For the students, thank you for attending. I know it's probably either wrapping up the semester, it's going to be finals week and whatnot. Best of luck to you on your exams. It's a true pleasure to introduce Dr. Shahab Mohaghegh, who is a faculty, a professor at West Virginia University. He also is the founder and director of a company called Intelligent Solutions. Shahab is, it's the first time we personally meet, but I've known of his work certainly prior to meeting him. He perhaps can be considered as a pioneer in the use of application of artificial intelligence in oil and gas. He's engaged with industry as he is in an academic sense. So when it comes time to the Q&A, feel free to grill him. Sorry. Without further delay, Professor Mohaghegh, all yours.
Thank you very much, Dr. Rami, and it's a pleasure to be here. Thank you for inviting me here to do this. So, the topic is AI-based, also known top-down reservoir simulation and modeling. What I will be covering first would be the difference between numerical reservoir simulation and AI-based reservoir simulation. One is top-down, one is bottom-up, and I will talk about that and explain how. After that, I would provide a little more information from top-down modeling, the AI-based reservoir simulation. As part of that, what we do is called geoanalytics, which is an AI-based geological modeling that comes out of the TDM or top-down modeling at the end rather than what we traditionally do at the beginning. This one comes at the end, and that's top-down explanation. We'll explain that as we go. And finally, I talk about another thing that we do. It's called AI-based dynamic production allocation, because we do production allocation as reservoir engineers. We've been doing it for the past 70 years, and what we do through AI is quite different from that, and I explain how that works. Okay, so if I'm lucky, I can do these topics by the time that we have. However, what I also have here with me, just in case there are questions or more time or more interest, I can talk about engineering application of artificial intelligence and machine learning, which is absolutely very quite different from non-engineering application of artificial intelligence and machine learning. That's one of the key issues that unfortunately a lot of people, specifically in the engineering, do not realize it. They think what Google does, we can do the same thing and get the results. What Amazon does, we can do. No, those are non-engineering applications. There's a big difference between these two. The general essence is the same. However, the way you apply it is quite different. And I can explain that in a lot of detail. Another thing that I could talk about, if time allows, is called intelligent data patching. What does that mean? That means every time you deal with numerical reservoir simulation, or every time you want a history match, or you want to do something about a field that has been around for a while, does it have all the data that you want? Well, 99.9% of the time, there are missing data. And the question is, how do you handle the missing data in order to do AI? There are a very negative and a very bad way that a lot of people do. And I can explain that, what I mean by that. What we do is we use AI to generate or to patch actually that missing data before we go any further. That's another key thing that we do. And finally, another thing that's very important is what's called explainable AI, XAI. And Another non-correct thing that a lot of people think that when AI is applied to engineering, then it's black box. And if you have written recent articles in SPE in March, that's one of the things they said in the definition of AI and machine learning. They called it a black box. Folks, if it's a black box, it's definitely not an engineering application. It is engineering application. It is not a black box. It's actually explainable. And I could cover that. And if the time allows, most probably the last three, we don't have time to do it, but at least I have it. If there's a question, I can go. So let's first talk about the difference between these two different approaches, numerical versus AI-based top-down model. First and foremost, the traditional numerical reservoir simulation includes assumption, includes simplification, includes interpretation, a lot of time, and sometimes it includes preconceived notion and some biases. AI-based reservoir model, it's purely fact-based. It's only about reality. The only thing that's used to build a model purely only is anything that it's measured, nothing that it's calculated. If it's not measured, it's not included. Traditional numerical reservoir simulation starts from geological model, which is 10,000 feet under the ground, and then it matches the production that is on the top, in the surface. AI-based does exactly the opposite. It starts from the surface. It starts from the production, operational conditions, wellhead pressure, wellhead temperature, choke setting, flow line pressure. It starts with that. And then when it's done and it's history matched, it provides you with a geological model. So that is the opposite detail approach. So let me explain that. So AI-based reservoir model takes an opposite approach when it's compared to traditional numerical reservoir simulation. Let's assume that this is a field, right? It's and you have the surface, and let's say this is the reservoir that we're trying to get the oil and gas from, right? What do? We drill the well, we complete it at where the reservoir is, correct? If that's the case, what do we do? What do we have? The top is where you see where the well is. The bottom is where the reservoir is. In numerical reservoir simulation, we start from here. We ask G&G people to develop a model for us. They give it to us, to reservoir engineers. What do? We start changing it until we get a history match. So we start with the bottom, we get the model of the geological formation, and then we try to history match what's on the top. So we go from here, so it's a bottom-up approach. So bottom-up modeling starts with the space. It starts with the space and brings in the time in order to do its history match. However, TDM, the AI-based, does exactly the opposite of that. We start from using the measured history productions. Anything that has been measured on the surface. As I said, oil, gas, water production, operational conditions, choke setting, wellhead pressure and temperature, flow line pressure, and then we go down and we history match that using every single measured, only measured information from every log, every core, even seismic information that we have at that level. We take all of that, we go from top to the bottom. I'm going to provide you a lot of more detail as we move forward with this. So top-down modeling starts with the time and then brings in space through field measurements. And again, everything is purely measurement. There is absolutely no calculation. TDM is based on reservoir. It's literally a reservoir management tool to a very large extent. If you are familiar, reservoir managers and reservoir simulators are not necessarily speaking the same language. TDM has very small computational footprint. You can run 10,000 times of it on your laptop in an hour or in 2 hours. That's why it allows you to do optimization. That's why it allows you to do sensitivity analysis. TDM can be executed in a laptop, and not right now, but hopefully in a tablet and eventually on your smartphone. TDM is a tool for field development planning and uncertainty quantification. I'm going to show you results that actually we got from it. So it starts with only field measurement, and it history matches it using real-time. And by the way, the history matching, unlike numerical reservoir simulation, history matching in TDM is completely automated. Completely automated. And another thing is you do not change anything at the level of the each well and at the formation in order to get a history match. And of course, you start this, you automate, it's an automated history match, you do production forecasting, you do field development planning, and literally you deal with that and you do all of that. And of course, that gives you an example. I'll show you more examples of how history matching and sensitivity analysis goes. So the definition of TDM is an AI-based, it's comprehensive, empirical, full field reservoir, unlike some people do it on a, if they have 100 wells, they do it one well at a time, because AI-based doing one well at a time is very, very simple. You really do not, I don't know why they call it AI, that's discrete, DCA. Anyway, so it's a full field, it's one model, but it's applied to every single well. And it's developed solely based on field measurement, well trajectory, log, a core, well test, seismic, operational condition, everything that is measured, it's used. And of course, the historical production and all the injection data. TDM is fast and accurate reservoir model, not its development, not its training, but after it's done, then it runs very, very fast and validate. And another thing that we do in TDM that probably a long time ago used to do it in reservoir simulation, no longer we do it, it's blind validation. And I explain to you what I mean by that. Because don't forget, if you make a simulation, what do? You give it to a company, and what is the company going to do? They're going to look at the future. They're going to find out if I drill a well there, what happens? Or in the next 3 years, this particular well, what's going to be its production, right? So if you cannot do that, right, then they're not going to anytime trust you. So the best thing you do, as I will tell you, when you want to do a TDM for a model and the reservoir that they give you started, let's say, in 2000, and they just give it to you right now in 2022, what do? The first thing you have to do is say, okay, we are not in 2022, we are in 2020. So you take the 2 years of the data and you put it away. You don't even use it in any shape or form in what you do. You build your model, you do history matching, you do forecasting, then you measure against what you did have or you didn't use. Why? Because that's exactly the company that you're going to give it to you. They're going to do. They're going to do it from 22 to 25, right? In the next 3 years. So you have to practice that. Is autonomous updated? And by the way, once you build it, then making it update, it's so quick, it's so fast, and literally you can do it in real time. One more thing, it's a coupled model. It's not only reservoir, as I told you, it's a reservoir plus wellbore combined. Unlike numerical reservoir simulation, in TDM, we do not need flowing bottom hole pressure. Why? Because it doesn't exist. 90% of such a data doesn't exist in mature fields. That's why we do not use it. Operational conditions such as choke setting, wellhead pressure, wellhead temperature, flowing pressure, and flow line temperature are the input into the TDM. Oil production, unlike numerical reservoir simulation, oil production is not an input to calculate flowing bottom hole pressure. Oil production is the main output of the TDM. In top-down modeling, these dynamic variables are simultaneously history matched together. Oil, gas, water production, reservoir pressure, and water saturation. How do? We start with the static data and with the dynamic data. We take that and we try to learn as much as possible. It is all about domain expertise, folks. It is impossible for you to do it if you're not a reservoir engineer. Okay, so first and foremost, just like you do reservoir modeling, you have to understand and learn as much as possible everything that you can learn from what happened in that, from the data, communicate with people who have done work in the past in order to know everything there is to know. And then you do intelligent data patching that I mentioned. Then you do dynamic conductivity mapping. I'm going to explain that. That's what creates the AI-based geological model on the bottom. And also that allows geoanalytics. All of that, we develop what's called spatial temporal database. Keep one thing in mind. One thing we learn as a reservoir engineer is that everything fluid flow in porous media has to do with not only space, not only time. It's about space and time, diffusivity equation, if you look at it. So you have to make your data such that, another thing, don't forget, what is machine learning? Machine learning is the tool through which artificial intelligence can take place, correct? Now, machine learning is learning, right? Is it possible for you all are reservoir petroleum engineers, right? Was it possible for you to become petroleum engineers if you were not taught, if there was no teaching? Because if that's the case, why did you come to the university? You come to the university because people teach you. That's how you learn. Is it possible for a machine to learn if you do not teach? If you think that I can provide the data to machine learning and it works, that's not called machine learning, that's statistics. That's been around for 120 years. AI, as we know it today, has not been around that long. It's been mid-80s that came in. So if the statistics could do what AI and machine learning can do, why didn't it wait for 100 years before they do what they plan or they say they're doing that? So that's the difference. If you only take the data and give it to the algorithm, yeah, you're doing statistics. But your job as domain expert is to get the data, develop it in a fashion that it teaches that algorithm what to learn. You're teaching because the machine is learning. Once you do that, you create that. There's a lot of detail about that I'm not talking about. There's a book written in this. I show it to you. You can look at it. Then you do an automatic history matching, which literally does this. You take this information, you go and you build the model that includes all of this, and then what do? You identify, you do blind validation, the data that you did not use to build the model, but you check it. You blind validate it. If the answer is not good, then what you have done probably is not good. You're going to go back and figure out what you have to your data. Another problem that people do is they think, oh, if this is a no, or if it's not what I want, exactly what I have to do. I have to go and change the hyperparameters of the neural network and polyset theory. Yeah, if you work for Google, you're absolutely correct. You should do that. If it's not engineering, yes, go do that. But if you don't get a 70% accuracy, then your problem is this. If you get above 70% yet, it's always good to go and change hyperparameters in order to increase and make it better. But if you don't get there, the problem has nothing to do with the structure of the neural network, the way you handle the neural network, that all of these things has nothing to do with it. It has to do with your way of communicating with that. And of course, when it works, then it can provide you all that results. So let's see what top-down modeling is. Building purely fact-based and coupled reservoir and wellbore simulation and modeling of a mature field is top-down modeling. What you use is well characteristics and trajectory, formation characteristics, logs, core, seismic attributes. What's very, very important, the details of completion and all the workover that has been done, anything that is measured and so forth. So it's fully automated history matching. That means no well-based modification to achieve history matching. For you to do numerical reservoir simulation, that's how we get a history match of numerical reservoir simulation. We change things around every single well. Another thing is oil production is not used as an input for history matching. It is used as an output for the history matching. And a full field reservoir simulation model history matched for although you build one model, that model applied with every single well in its entire history to history match. I'm going to show you. Then we do blind validation, which is a tail end of the data that left out. As I mentioned, you take it out, you don't use it in order to blind validate it. And of course, once you do that, then you forecast it. First you do production forecasting, then you do optimization of OPEX, and then you can do optimization of CAPEX. Identify where to drill the next one. I'm going to show you an example of that. So this is an example of a mature field in Southeast Asia. Since that company published it, not me, but they did publish it, so I can share it with you. That's the SPE 216093. So here's it's a very, later on we found out that they used this field with numerical reservoir simulation for more than 10 years, and they could never get a history match. That's how they asked us to do it. So it's multi-layer, it's offshore, and there are platforms, and these are about 14 different layers. These are the 4 platforms that you see in the field, and this shows you oil production, gas production, water injection, and gas injection, these colors. This shows you the production records for every year from started from 1991 until when we did it in 2017, how much production was done. And of course, these were the data that was available in choke, wellhead pressure, and wellhead temperature, the amount of it that was available throughout the time. This is what we did. As I showed you, we used both static and dynamic. So one of the key issues, as I said, it's very important for you to communicate and teach is offset wells. In other words, as you are very well known as a reservoir engineer, in every well that does everything, it is impacted by all these wells around it, whether it's an offset, whether it's a producer or it's an injector, in both cases. So you have both cases for that. And this is Reservoir Conductivity Map. I'm going to show you how to a second and how we do that. What does that mean? That literally tells you the communication. Yes, there's history, there's a heterogeneity in pressure, in saturation, it's in pressure, in permeability, in many reservoir characteristics. When you put it all together, then I tell you how we do that in a minute. It tells you the changes that takes place. When you say high in the red, is that communication between the wells that exist in those areas are much faster with each other, and when it's blue, it's less. This is for the entire field. This is for 3 of the groups of layers that they had. We did it for them, and here's what we did. This was when we started. That was when we get the project. So we identify a certain amount of it, and then you take this and you put it away. This data is in no shape or form is used to be building the model. We remove that for blind forecasting. Then we take the rest of them. The rest of them we divided in 2 pieces. One is for history matching. The other one is called blind validation in time. So literally, first we do this, and then we see if the forecast that we have done is good. In that context, let me show you the results. There was, this is an example of one of the wells. The dots that you see are actual data. This is the blind validation. This is the data that we did not use at all to build the model. This is the history match, and that of course shows you the Q. Now, if you zoom on that part only, you can see more detail how the history match was done. And this is for one of the platforms that we have done. Going to more detail, this is the actual gas and TDM, GOR, and this is water cut that was done for this field. It's not very good, but it's not bad. This is platform 1, platform 2, platform 3, and platform 4 that we did for history matching for this particular field. And when you see that, we done it for, but it's applicable to every single well. This is one well, that's the location. This is its oil production. That includes the 4 blind validation. This is gas production. This is water production, and this is water saturation and reservoir pressure. There was very little data from it, but nevertheless. So one of the things I would like to show, let me show you one more thing. This is the blind validation in the forecasting that we didn't use for these several wells. And as you can see, for some wells, it was very, very tough to do it. This had to do with this particular field, but nevertheless, and they asked us to do long-term forecasting. This is what we did, long-term forecasting for a specific platform for oil, gas, and water. So, and of course, this is for the entire field, but this is for a specific well in a specific location. This is another well that we did this for. So I want to show you one more thing. I'm going to be very, very quick on this. This is another field that we did that in 2017. This is, we just did it. Actually, we're getting better in this on a regular basis. This is also in the Southeast Asia, and it's also offshore. And we did it for a field, offshore field that looks like this. It's actually 2 platforms. This is B, this is E. And I'm going to just very quickly show you the entire field with the 3 years of blind validation. These 3 years were removed from, we just did it for this. This is oil. So we just history matched this and forecasted this, and you can see the result. This is for the entire field. This is oil, gas, and water. I'm going to just show you, because I showed you only one well. This applied to every single well. I'm going to go through it. You see where the well is, okay? And then you see the results. I'm going to go through it very quick, so it don't take more than 1 minute, but at least you can see what we did on a well-by-well basis. This is one well. This is another well. This is another well. This is another well. Just wanted to show you all of these wells that we have done to see how far we went from 2017 to now. Some of them produce really no water, and TDM catches that as well. A few more and I'll be done with this. Then I'm going to show you some actual results. These are forecast results. I'm going to show you some more results in a minute. I think this is it. Okay, so now I'm going to show you some of the work that we have done for some of the companies. This is actually, it's called Buhasa. They allowed us to share this. This is Buhasa. We did this in 2011. All right, this is half of it actually. This part. And we did it in 2011, and we were finished. And then in 2015, 2016, they came out. They wanted to give us another project to do. Buhasa is ADNOC in the United Arab Emirates. And we said, sure, but they said, okay, before we give it to you, we have to do one thing. I said, sure, what is it? Said, you did Buhasa for us, right? I said, yeah. Said, do you have the data, the model? I said, yes, we gave it to you as well. You have it too. They didn't know where they had it actually. And they said, okay, since then we have drilled 23 wells. We're going to give you the location. Can you tell us when we drilled the well, what was the reservoir pressure and water saturation at every well, the location that we did it? I told them, after 5 years with no data, I can do it, but I don't think these results is going to be good. They said, no, please do that. So if we get the result, then we can. And I said, I do it on one condition. And that is, if I give you the result that we do, would you give me the result that you actually measured? Because you're not going to give it to all, you're going to give me the location. So I know how good or bad we did. They said, yes, we'll give it to you. And here's the results. There was 5 years after, 23 wells. These 23 wells, I call it stress test because we've never done this before now. So there was 5 layers. The total was 23. And this is the result that they did. 35% of the wells were more than 95% accurate pressure. 26% of them was between 90 to 95% accurate. Put them all together, 90% of the TDM productions were more than 80% accurate 5 years after the model that was done. And they asked us for water saturation, 70% of TDM predictions were more than 80% accurate. That was one item that I can share. Another thing that I can share, it's another field in Caspian Sea that another company was doing that, and they wanted optimization through choke setting. So once we did the TDM, we used 15 wells, and we told them what they need, what the choke setting they had, and what they should do in order to increase production. They tested, actually we did more than 15, they tested 15 of them. Out of the 15, 2 were wrong, the other 13 were correct. This is the email they sent to their bosses that says the result was correct. Once they did the test, they actually did it on 3 wells. They changed the choke setting as we asked them, or that we recommended. Those 3 wells created that much barrels per day increase, literally 189 barrels per day, which in the time that was $5.2 million that they made at the time, the cost of the work. Then they also did the forecasting. This is, we forecasted this, and then they tested it, and this is the result. This is not what we blind validation was, they had done it. And I have one last thing to show you on this topic, and that was in the same field, they had 3 wells most recently that they were identified by numerical reservoir simulation using Eclipse, a consulting company, to tell them where to drill. And they had drilled, and they asked us to tell them by TDM where to drill. And this is what we told them. Literally, these are the 3 wells that was done by, this is the entire field, right? This is the, comparing this within these 3. What I'm showing you here is not from me. One of the top managers in 2020 ATCE was in a panel session. He mentioned that, and he brought it up, and I was shocked, to be honest with you, because he hadn't told me that. Then I went to him and said, am I allowed to share with people what you just put here? He said yes. And here's the result. Let me show it to you. So first and foremost, we're going to talk about the average production rate during the first 6 months of production in barrels per day. The first one was 28. It was drilled in February 2013, which is 86 months from April 2020 when we got the results from them. And the first 6 months, this is how that well did. This well was done in November 2014, 65 months. That's the first 6 month average that well did. This one was in February 2015, 62 months. That's the first 6 months that well did. This is when we did this for them in June 2018, they drilled it. That's what the first 6 months that well did. And by 2020, total production was 22 months. Then we compared 6 months and we compared the 22 months for every well. Here's the result of the 22 months. Okay, so what time do I have to stop? Okay, very good. So with that, the results that I showed you, now, remember I told you when we do TDM from the top, then we identify what is the geological formation in the bottom. We call it geoanalytics. So let me explain to you how we come up with that. We do AI, we call it AI-based geological model. So initial geological model is developed first to start the numerical reservoir simulation. This has been going on for the 75 years. In AI-based geological model is developed using production history. So it goes exactly the opposite. The major thing in initial geological modeling is spatial interpolation. When they get two values, they interpolate spatially. The difference between AI-based is not, it does the same thing, but its interpolation is not spatial, it's spatial temporal. Why? Because everything that happens in the production tells you something about the reservoir. Let me show you how we do it. So originally, geological model is developed, and then it never results a history match, and it must be significantly modified to achieve history match. So history matching of numerical simulation is usually a very long process. So what do? You get the original geological model, you history match it, you never get a history match, there is no match, so what do? You change the transmissibility. Every numerical reservoir simulation software that you use, CMG, T-Navigator, Eclipse, they don't tell you to change porosity, permeability, and thickness. They change, oh, click here, you can change the transmissibility around the well. What is transmissibility? Transmissibility has to do with porosity, permeability, and thickness. So they allow you to change it without you. I'm sure you realize that, yes, I'm changing everything that I've actually measured. You do transmissibility modification on a well-based, and you do that, why? Because that modification, how much do you do that? You do that over and over and over again until you get history match, right? When you are successful, then your new geological model is very different from what they've given you, right? And of course, when it's successful, then you can use it for production optimization. So, geological model uses the original geological model. They use the actual data, no doubt about it, but they make assumptions and they make interpretation. And they use it through spatial interpolation. And they use Kriging or radial basis function for spatial interpolation. What I mean by that, if there are these three wells, then they have this porosity, and say, okay, between 4 and 10 and there's 4 and 16, then between 4 and 10 in the middle should be 7, between 16 and 10, the middle should be 13, between 4 and 16, the middle should be 10, right? And when they do that, actually, when you apply that, when you have so many wells, this is actually a real field, the one that I showed you, the result in Southeast Asia. So these are all the producers, and these are the injectors for the well. And so what they do, they identify the location, the distance between them, and they say, that's how the distance between them, and that's how they come up with this distribution of gamma ray, because they have the values here, and they spatially can do the difference here, right? Okay, now let me show you what we do. So geological model is developed using spatial interpretation. AI-based geological model is done using spatial temporal. How does that happen using space and time? Let me show you. We use static data, we use dynamic data, we use what we call fuzzy pattern recognition. And if you're interested in that, all the detail of it is shown in my book called Shape Analytics, of how we do fuzzy pattern recognition. So you do fuzzy pattern recognition and you do dynamic mapping that I showed you earlier, and then using those two, you generate a spatial temporal interpolation, and that provides geoanalytics or distance model. Let me give you an example on exactly what I told you. So these are the existing production, these are existing injection. You first start with the injectors. Every injector is impacting all the producers that are close to it. So this injector is dealing with these, this injector, this injector, this injector, and this injector, and you put them together. This is the communication of the injector with all the producers that surround it. You're not done. When you do that, you go to every producer, and every producer is impacted to a certain, that's the idea, to find out that every time base, time step, production of every single well, how is impacted by the others. So this one has impacted by that other offset. So I'm going to go through it, and you can see every well is impacted by all others. You put them all together with the injectors. That you have the information, then you use that information to an artificial intelligence to give you the conductivity, the dynamic conductivity of all these communications with them. Then you use that in order, and how do you do that? For example, let's assume that this is, so if you have 100 wells, every well is a focal well in your analysis, and every well has so many offset wells. So every focal well that you deal with, let's assume it has three layers, right? Layer 1, layer 2, A, B, and C. So, and that's not enough. You also have to know how this is on a time step basis every month. You have to identify how much completion it has in every layer. And you know the completion is modified. Sometimes they stop it, sometimes they create more, and so forth. Then you go to the offset wells and you identify the layer distances and how they communicate, and then go to the completion. And then you find out the completion between them. And that's literally what tells you, so this is for one well, this is for another offset wells, you do the same thing for them. And when you do that, this becomes, for what I showed you, this becomes the conductivity map. Using what I just showed you, this shows you the conductivity map, how the low conductivity to high conductivity from blue to red. Now, what do we do with this? We take this, we'll go to gamma ray. In gamma ray, if I don't use that conductivity map and use only what is spatial interpolation, this is what I'm going to get. However, if I use that instead of spatial, space and time, I'm going to get that. You see the difference. If you go to porosity, in all of them, I'm going to show you the conductivity map here that stays the same. But you see how different becomes porosity distribution with space and with space and time. Permeability, the most important was this for us, initial water saturation. And what you're looking at, the time goes on. Color changes. Literally, it tells you, it allows you to identify, if you have original oil in place, it tells you the distribution, where is it? And then for every, so let me go ahead back, and it goes from the beginning every month. As you can see right there, every month it goes through, and you can see the recovery factor, and you see that the darker the color, the more oil is there, right? So let me go back to show you, and watch. Every well that comes in every time step, it changes, then it provides you where the wells are. That's how we find out where to drill. Is that enough? No, you need to do that for pressure as well. This is the same thing, again, for pressure distribution. And then you put the pressure distribution and amount of oil together, that tells you, remember I told you where to drill. AI-based dynamic production allocation. How do we do production allocation, folks? In the past 70 years in oil and gas, permeability and thickness of each reservoir layer is identified and multiplied by K. We call it KH. We take the KH, and production from each reservoir layer is allocated based on the KH of that layer, right? The fact is, fluid glucose media is about space and time. K and H both are space, has nothing to do with time. And when we do the same thing with AI-based, we bring in time again. So we say a separate, we do literally separate TDM for each reservoir layers, and then TDM is a function of both space and time, and then our production allocation is both about space and time. Let me give you an example. What you're looking at, folks, how do you know if you're right or wrong? I'm sure you know there's this thing called PLT, production allocation, that they do as a function of it. They do it and they identify how much oil is coming from which part. In the history of our industry, never two PLT has been done on a field at different time and gave you the same percentages. Never. So what you're looking at, this is B1, this is B2, this is B1, based on the percentages that they are in KH. And when they did the, this is when the PLT was done. So you see, says PLT says 2 is here, but it's actually here. It says 1 is here, but 1 is here. So it doesn't apply. When you do the same thing with AI, look at the difference. And all of this, I've put them all together for this particular well. You can see this is what the AI says. This is what the KH says. This is what AI says, KH says throughout. I have done that for several wells. This is for another well. You see? For this well, it says B2 is this one, B1 is this one. What they do in this time that they did PLT, this is the 2. And when you do it with AI, this is the difference. And when you put them together, the same thing. This is another. You put them together. This is another one. Look at the difference here. And look what the AI did. This is so literally that ends what I wanted to present because it's 17. If there is any question on those ideas of the difference between engineering, that's one of the unfortunate things that's happening. I was talking to Dr. Yunus here today that it's very, very unfortunate. And unfortunately, a lot of people in the business in the United States, they really don't like me at all, honestly, because I tell them the truth. Because one of the things people do, they use AI in the oil and gas industry, and now in other engineering, I learned that the same is true in mechanical and chemical engineering. They use it as a marketing issue and as a business issue. The least that is important to them is the scientific application of this. Because the idea of AI is so sexy right now that they go to the top people in the companies and they get incredible amount of money from them, and then the results are so poor, and then the conclusion is, AI is not a good thing. Why? We just paid $10 million, we didn't get anything. Well, the way you did it was wrong. You did it to the wrong person that they said they AI experts, which they're really not. Unfortunately, there's either AI experts and they don't know anything about the domain expertise, which that's a problem, or they are domain experts and they understand the mathematics of machine learning, which is incredibly simple, and they think, oh, if I know the mathematics of machine learning, then I'm an expert in AI. No, it is about philosophy. It is about, I always tell my kids that how do you judge that you became as a petroleum engineer, as a mechanical engineer? How do you judge that you became an expert in AI? You know what my strong recommendation is? Find yourself, if you become incredibly interested in evolution, find yourself that you become incredibly interested in neuroscience, and you become incredibly interested in philosophy. If you didn't get yourself so interested to go in those directions, then you have a long way to go. If it takes you 30 years, 20 years, 10 years to become an expert in reservoir engineering, folks, why do you think it's going to take you 10 days or 10 months to become an expert in AI? It's the same thing. It's going to take exactly the same amount of time, same amount of research. Don't get up. You don't do it really well, don't get upset. Keep doing it. What did you do in reservoir engineering? What did you do in petroleum engineering and everything you did? The same thing. Let me show you one thing. You think I'm joking? I'm not. Let me show you one thing. Let me see if I have it here. No, I don't have it here. Oh, yes, I do. Watch this, guys. What do you think if a company comes and it says, we create a master reservoir engineering in just 1 month? What do you think?
Super.
What do you think if another company comes says, we create a master petroleum engineering in just 1 month? We create a master mechanical engineering in just 1 month. So I just made this up. Or we make a master physicist in 1 month. This is nonsense, and nobody ever says that. Nobody ever, I just made this up. Why did I do that? I wanted to show you, does it make sense to you? This is not real. No company in the world have ever said such a marketing process. How about this? This is true. This is actually, I put this in the company. I can tell you which company. Google it, you find out. This is true. This is what they do. That's what my problem is. And if you think I'm kidding, I'm not. This is very, very, very true. That's very unfortunate, but it's very, very true. My key is to you as a student, take yourself very, very serious. Deal with AI the same way that you deal with coding, with reservoir engineering, with drilling. How long did it take you to learn and be good at those? That's how long it's going to take. Don't think just because I know the math of this. Honestly, the mathematics around in the bottom of machine learning, you don't need to do a master's degree or a BS. With a high school diploma, you can, because the mathematics is very, very simple. The mathematics of neural network is very, 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 very simple. Some of them are more complex, but it truly is very simple. And you don't even know it, because why? Everyone want to code it. There's libraries in Python. There is TensorFlow. You don't even need to do that. Then you bring it in. But it all has to do with how you think. How do you teach? How do you teach a machine learning algorithm about reservoir engineering? Everything you learn, you have to cook. And there was one problem. In reservoir engineering, when we go to class, we think they know math, right? And we start, or they know physics, right? But the fact is, the machine algorithm doesn't know math, doesn't know physics. You can't even speak English or Arabic or any language. You have one thing, that's data. So communicate with the machine learning algorithm only using data and teach it. Teach it reservoir engineering through that data. Remember the offset that I told you? If you only concentrate, you're doing it for the entire field. If you're doing only on one well, how about everything that's going around it? Think about everything you learn. But thank you very much. Stop talking. Yes, please.
What type of machine learning model do you use when you want to forecast?
Same thing that we use through history matching.
So you use neural
networks, yes. We
So,
use a combination, actually, to be honest, a combination of neural network and fuzzy set theory.
So you said that AI is fact-based, but you're using neural network where you maximize the likelihood of the data. You use maximum likelihood estimation or maximum posterior estimation.
No, we don't.
So how do you train your model?
We use the data that exists.
No, what is your error function?
Loss function.
What is your loss function, the error function?
What the neural network calculates versus the actual value that we go to train it.
So that comes
Subtract,
from
you this minus this gives you error. When you do it for the entire epochs, It uses it as a loss function and creates the back propagation.
So that comes from the maximum likelihood estimation. And the maximum likelihood estimation is based on probability, so that has.
Absolutely not.
No.
It's based, no, it comes based, it's not a probability at all. Probability is a statistics problem.
No, what I'm saying
Number
is,
one.
the error function, the loss function is the conclusion of maximum likelihood estimation.
Absolutely not.
You
It's not
can
an
watch the
estimation.
you can watch the machine learning course on YouTube. There's a Carnegie Mellon University course in 2015 that discusses.
Why do that?
How-
Let me tell you what we do. It's 1 + 1 = 2.
Yeah.
That's as simple as it is. You have, let me show you. I'm gonna make it very, very simple. Let's say I have 1, 2, 3, 4, 5 inputs, right? And they're actual layers, they're actual data that was measured, right? This is your hidden neurons, as many as you like to put. This is your oil production, right? This also is calculated in the actual data, correct? So these are communicating, right? There's all of these are, so let's say we have 1,000 cases, right? You take these 1,000 cases, every one of them calculates a value in this step. It's called epoch. In the epoch 1, all of the values of these weights are random, right? It calculates this, it gives you a value of whatever oil production is. And then you say, okay, this is wrong. Why? Because the actual oil production was this. This is the error.
Yeah, no, that error to 2, right? You say error minus the true value to 2. You don't say, for example, to 5, or you don't say to 1, right? You use maximum, for example, you use mean squared error function, right? You cannot use that because
That's what we
of that, where you need to square that error
Sure.
function.
Sure.
So in
But
that,
it's from the calculation.
yeah, no.
Based on these-
My question is, how did you write that error function? That comes from the maximum likelihood estimation.
There is no estimation. What are you talking about, estimation?
So
All
I'm
of
talking
these-
about the theory of neural networks. So when you write that, you're doing maximum likelihood estimation. Because you're writing the probability of data with respect to your parameters.
No, everything you're doing is based on actual data.
No. I'm not talking about applying that. You're applying that model and you use that error function, that's fine. But what I'm saying is the theory behind that is based on maximizing the likelihood of the data.
So what he's saying actually, yeah, I think you're right too. So you have a kind of a loss function, right?
Yes.
List squares.
Yes.
That comes from actually, if you look at it, comes from the statistic maximum likelihood estimation. That's what he's saying, and to maximize the probability. Okay? So that's okay. I have
This error tells me what is how
So
bad.
how the weights are determined based on minimizing that
Exactly.
objective function that comes
Exactly.
from the maximum likelihood estimation theory.
Yes,
So that's
you know where that comes from.
Yeah.
That comes from how synaptic connections in your neurons act in order for you
Well,
to
that
feel
comes
the way you
from
feel.
that comes from Gauss too, actually. And that's it.
But anyway, and then.
Yeah, but I would like to ask
Sure.
a few questions. Okay,
Sure.
so you said conductivity map.
Mhm.
So what is the units of conductivity that you are defining, and how do you quantify that? I mean, how do you come up with a conductivity map? That I wanted to learn. Yeah. But it looks like a very interesting map.
Things that we come up with,
Hmm?
things that we do. Let's assume you have 10 years of production. And let's assume, based on the data, the time step that we use is monthly, right? So 10 years of 12 months, that gives you 10 times 12, 120 time steps for everyone, right?
Mhm.
So for every well that you're dealing with, you have oil, gas, water production, you have wellhead pressure, you have choke setting. A lot of times you don't have wellhead temperature, but all of the field measurement that you have, You bring them together, and for every well, because every well is a focal well, and it's compared to its offset wells. So if you notice, the offset wells are not necessarily two. It has to do with the shape that tells you how many they are, right? So literally, these are the data that you use is all the production, all the operational conditions, and the completion.
Well, my second question is, okay, when you compare gamma ray data with the, what you call it, spatial temporal map.
Yes.
I mean, I forgot my formation evaluation knowledge, but gamma ray is a static measurement, right? I mean, gamma ray, it's static. So how do you compare? I mean, is it fair to compare static data map with a dynamic temporal interpolation that you use?
Very good question. Very good question.
Time varying data.
Very, very good question. What I'm doing, I'm not saying gamma ray is not static. That's not what I'm saying. Let's assume I'm a well, and Dr. Yunus is another well, right? Measurements of me is not going to change. It's the same. And it's, as you said, it's static. The same is true for him. How about this one in the middle that I haven't measured? The question that we ask, that how can you make a judgment, this value at this location between these two measurements, what is it? What does it has to be? The only thing we're saying is, okay, the only thing we're saying is what it tells me about communication between us, because that has to do with let's assume you're another well, and these are the three wells, right? The question is, the communication between us is the same as the communication between you and I? No. Because even I'm closer to him, maybe you and I can much quicker be communicating than we do. Why? Because maybe what's happening in static between us is going to be very different from the gamma ray. The gamma ray between us is going to be different between gamma ray between you and I. How do I know that? The only thing I'm saying, and I'm not saying it's 100% correct, but I'm saying it's the only thing, it's not assuming that whatever between you and I has to do with our distance. I'm saying no, it's not only about our distance. Distance is important. However, it has to do with when you in the past 10 years produce and I in the past 10 years produce, how did we communicate? And the same is true between you and I. That communication, by the way, we don't put the state away. We don't put the space away. We just keep the space as is. We bring the time to it. We bring them together. Instead of spatial, we make it spatial temporal. That's it.
In your example, Southeast Asia, where you're so complex faulty, did you have enough history you were able to identify blocks that were actually sealed by faulting versus ones that were not?
No, not there. But what we did, it was very surprising to us, actually. In Mohaghegh, we did that. Actually, I could show you the distribution of water saturation as a function of time. We showed that to the people that were presenting, that were showing at the end, and they were GNG people who didn't know what we have done. And then they said, the fault that you showed makes perfect sense. And I said, what fault? So didn't you put the fault? You gave me the seismic. I know you didn't give me seismic. I didn't put a fault there. But the fault was there. In other words, fault is not an interpretation of us, but the communication between the wells brings it up. They haven't had that anywhere but in wells.
That's what I was thinking when you were discussing with him, how we interact.
Yeah.
Because you wouldn't see the interaction if you had a clean sealing fault. You would see the boundaries.
You're
as
absolutely
the well
right.
saw the boundaries.
And that's exactly the case. Again, between you and I'm so close to you. If there's a fault between us, no matter how good we are together, you cannot impact me, I cannot impact you. You came so far away from me, there's no fault, and our interaction's a lot better. So that's why when we compare us, and there's no communication between us, we plot everything, instead of being like this, is literally like this, we're like this. that means there's nothing going on between you and me. But there's something going on between you. So this is the space and the time tells you a lot of communication.
Now, in traditional modeling, you were limited by cell size, by the computing power. Does that float with AI?
No, we don't use any cell. There is no cell.
There's no cell phone?
No, no, not in people. In the smart proxy is, which is AI-based in numerical reservoirs, which is a completely different story we talked about.
Shahab, I've got a curveball question for you. You mentioned philosophy a few times. One thing about learning is learning from mistakes, right? The data that you're training to, that you're training, probably all obeys, the second law of thermodynamics, right? So how can your machine also always obey the second law?
I'm not sure if I understand.
So to make it simpler, just a simple pendulum with a mass. We believe in the laws of thermodynamics.
Okay.
And if I use observations of that pendulum ad infinitum with a theoretical universal approximation, a topology, a certain family of networks of infinite size, sufficiently capable of representing stuff, and I train it to these infinite, to this infinite series of observations of this pendulum, can I guarantee that your network in prediction will always make predictions that honor
Very good question. One of the conclusions that we have come up with is what's called I'm getting old, I forget words a lot.
At infinity, probably yes, right? But what is infinity and how do you define it? Less data, less observations. A finite network, smaller. What's that? You see what I mean? Going back to statistics, I mentioned that I grew up in the modern applied statistics view of things, so I apologize for that. But when you look at it, essentially, it's an issue of I don't know, maybe fitting and then extrapolation, constraints, and that sort of thing. So what's unclear to me personally with learning approaches, and I haven't seen people trying to answer that question, is how much is enough? How many observations?
Yeah.
What sort of sample?
It's very, very hard to have a judgment on
to
that.
discover essentially the laws of thermodynamics.
It has to do, that's one of the key things about using AI, is it is incredibly tough, and to me, to a very large extent, incorrect to make a judgment before you know what is it that you're gonna do. Because once you identify the objective that you're trying to accomplish, then your domain expertise start telling you, and believe me, it's not gonna happen the first time or the first 10 times that you do it. It's after maybe a few years of doing this, you learn that you find out that the objective that you're trying to accomplish tells you a lot about what you need. Another thing that's very, very important, the difference between big data and non-big data. So when they say big data analytics, is it the same for when you don't have big data? The first question is, what is big data? What is big? Is it 1,000, 10,000, million, 10 million? What is it? And that is the way you deal with the machine learning algorithm to a very, very large extent has to do with what is it, what are you trying to solve, and how much data that you have. It doesn't mean just because you like to do AI, then you can deal with no matter what. No, that's not the case. One of the good examples is what we today call AI, and a lot of people our young people are imposed to it, to a very large extent has to do with what? It has to do with what Google did in 2005, 2004, which was image recognition. And they generated what's called convolutional neural network to do that. And it was fantastic technology, it is. And I make all my kids to learn it. However, please make sure there is no way on earth that you can use convolutional neural network to solve engineering related problem. Why? Because how much engineering did you learn from pictures? No. Even the distribution of pressure and saturation, which is a picture, where does it come from? From another picture? No, it comes from calculation of cells of pressure, and then you put them together, you generate the picture. So the idea is, or another one is LSTM. Where did LSTM come from? Why people use LSTM to do decline curve analysis? First and foremost, why do you want to do AI-based decline curve analysis, for God's sake? Decline curve analysis, I've been teaching it for 20 years, to be very honest, but let's be serious. Decline curve analysis, all you need is a pen. You don't even need an equation. So why do you need AI for that? That's, to be honest with you, and then people use LSTM for that. When you use LSTM, you know what you're doing? You're saying the heck with the space. The only thing I care about is time. That's decline curve analysis, isn't it? Decline curve analysis tells you exactly what the production is, and then you take that and build an equation, and it tells you what is going on. Right? So that's the problem. When you go to the engineering area, then you find out, okay, how can I deal with this? And without these two issues together, it's almost very, 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 very tough. So when you deal with somebody who's an expert in AI and machine learning, try to learn from them. Why? They spend 10 years, or they spend the same amount of time you spend on reservoir engineering, they spend on AI. That's why they are so good. They're not as good as you in reservoir engineering. You're not as good as them in the AI. If you can bring them together and work together and learn from each other, it takes time. It's not overnight. But that's a very positive thing. That's a very good thing. But never forget that if as a petroleum engineer, mechanical engineer, chemical engineer, if you want AI is a future for you, which is going to be the future of your life, then learn how this technology works.
All right, maybe one last question.
Yeah, I always have questions when I do the simulation. Did you consider about maybe there are some data wrong in the...
That's wrong.
Yeah.
Yeah, absolutely.
How could you distinguish it?
Okay. In order to answer your question, I thought, because everybody always asks that question, what I'd like to do is to ask you a question, if you don't mind. And based on your answer, I'm going to tell you what the answer is. I'm going to show you something. Do me a favor. Can you please read this? I'm not Chinese, so I don't know, sorry. Okay, so question, is that good data? Why couldn't you read it?
That's called pattern recognition in psychology.
Very nice. Another thing I do, do you mind? Wow. What was that? You know the equation for that, right? There is actually an equation that they build missiles, right? What they do is they say, okay, I'm going to throw this here. Where is it going to come down? It's It's gonna come down here, right? If you have the initial velocity, the theta, the gravity, then you know where this comes in. And there's an equation. I have a question for you. What I just did your brain build that equation, solved it, and told your muscle where to move to catch this?
Probably not.
Definitely not. In football, the kid throws and the guy goes and catches it. Those receivers that they catch, do they have a Ph.D. in any engineering? No. So how does the key is, how does human brain works? Human brain solves some physics-based problems without building an equation, without using exact, did you know what was my initial velocity? What was the angle? No. When you're driving and you see yellow, the green light turns to yellow, do you know exactly your distance? You just know it's far or it's close. I should go fast. So human brain deals with data that's not exact. AI actually, what is the definition of AI? Artificial intelligence, it mimics human brain. That is why you don't need 100% the way we need it in physics. Traditional physics, yes, we need good data, absolutely fantastic. But in AI, no, you need data. You need necessarily, doesn't have to be exact data. To be very honest with you, the first time I did the smart proxy for the numerical simulation, you know what we did? We were afraid of the actual great, fantastic data that come from simulation. What we did, we added 5% change to it, so it would be easier for the training process. But that's hopefully answers your question.
All right. Thank you. In the interest of time, let's thank you.
When we do this,
I don't think anybody's gonna say no. If you to say no, you said you want to provide PhD.
Oh, no.
Coordinating.
I'm
Thank you.
scared to tell. I'm worried about the board.
There you go.
Okay, Sean, thank you very much for
Thank
your
you very much.
presentation.
Pleasure.
Very